Okay, let's unpack this. We're doing a deep dive into an absolutely amazing paradox right now.
It really is.
It's how human ingenuity has made oil supply, virtually endless, while at the very same time, economic and environmental pressures are making that supply yeah, increasingly redundant.
It's the ultimate tension in modern energy.
Right.
Our source material gives us these two completely distinct narratives that are just clashing in the market.
Right.
On one side, you have this incredible, almost molecular level technical fight to squeeze every last drop out of old, stubborn reservoirs. That's enhanced oil recovery, or EOR.
And then on the other side, you have the, I guess, blunt force of a technology like hydraulic fracking, which didn't bother squeezing old wells at all.
Yeah.
It just unlocked entirely new, massive resource bases. It just radically increased global supply.
And the combined effect of all this is that the entire energy conversation has fundamentally shifted. We're no longer operating under the fear of peak oil, the worry that we will run out.
That's gone.
Now, the strategic concern is peak demand. The worry that the world will stop needing oil before we can even sell what we've already found.
So our mission today is to trace this evolution. We want to understand how these technologies redefine what available oil even means and what those new constraints, economic price ceilings, deep field technical difficulty, and of course, aggressive climate goals mean for you and for the global energy market.
And to really get the solutions, we have to start with the problem, which is the fundamental inefficiency of traditional oil production.
Yeah.
When you hear that an oil field has been depleted, the critical thing to realize is that it's nowhere near empty.
That was genuinely surprising when I saw the data. We put in all that effort and we get what percentage out?
Not much. The average recovery factor worldwide, using just basic drilling and secondary methods like simple water flooding, it sits really low.
How low?
Typically between 20 and 40%. Now, to put that in perspective for you, compare that to a typical natural gas field, which often hits recovery rates of 80 to 90%. We leave the vast majority of the oil permanently trapped underground.
So why is oil so much harder to get out cleanly than gas? What's the physics of that?
Well, it boils down to two main challenges that EOR engineers have to overcome. One is at the microscopic level, and the other is at the macroscopic level.
Okay.
First, you have the pore level challenge, just getting the oil out of these incredibly tiny, intricate pores within the rock itself.
And the main enemy there is surface tension.
Exactly. It's called capillary trapping. I mean, think of trying to get the last few drops of coffee out of a plastic straw. The liquid is basically held hostage by the surface tension sticking it to the sides.
So the oil droplets get stuck.
They get stuck in the tiny crevices of the rock, and the water you're pumping in just flows right past them.
So to fix that, you've got to find a way to make that surface tension just disappear.
What? Precisely. The surface tension between the oil and the displacing fluid, it has to be reduced to almost zero. It's a huge technical ask. If you can't overcome that tiny force at that tiny level, the oil just stays behind.
And the second challenge, that dictates how much of the field you even reach in the first place.
That's the coverage challenge. This is all about how much of the overall volume of the reservoir your injected fluid actually touches. If the geology is complex, and it always is, water tends to just channel straight through the easy high permeability zones.
The path of least resistance.
Right. Engineers call them thief zones. The fluid just bypasses entire oil-rich sections of the reservoir.
And this is the double whammy that really compounds the problem.
Yeah.
I appreciated the simple calculation in the source material.
It's a great illustration.
Right. If you manage a respectable 80% efficiency at the pore level, and you only manage 80% efficiency in terms of area coverage, the overall recovery factor is still just 41%. It really highlights how tough these fields are.
It does.
So given that fundamental difficulty, engineers have had to design some incredibly complex solutions. The whole field of enhanced oil recovery is a fascinating attempt to solve these microscopic and macroscopic problems with chemical and mechanical force.
Let's start with a classic EOR approach, miscible gas injection. The engineers realize that water can't destroy the surface tension, so they inject a gas, often CO2, at very high pressure.
Until it becomes miscible.
Right, until it becomes fully miscible with the oil, it dissolves into it.
It dissolves the oil, so there's no surface tension left.
Correct.
What?
When you remove that interface entirely, you get fantastically high pore level recovery. I mean, sometimes leaving as little as 2% of the original oil behind in the pores that you've contacted.
It solves the microscopic problem completely.
It does.
That's so. Well, why isn't everyone just doing gas injection? There has to be a catch, and I'm guessing it involves that macroscopic challenge you mentioned.
That is the problem. Gas is much less viscous and much less dense than the oil it's trying to displace. This leads to two major problems. Gravitational segregation, where the gas just rises to the top of the reservoir, and something called viscous fingering.
Fingering.
Yeah, where the gas just channels right through the oil instead of pushing it evenly, like pushing your fingers through a dense fluid. So you might recover 98% of the oil you touch.
But you only touch 30% of the reservoir.
Exactly.
Which leads us to the smart compromise, and probably the most widely applied conventional EOR method, water alternating gas, WAG.
WAG is a really elegant solution because it addresses both efficiency problems at the same time. You inject alternating slugs of water and then gas.
So the gas does its job on the surface tension.
And the heavy water acts like a piston, improving the overall coverage.
Yeah.
The heavier water tends to slump down while the lighter gas rises, giving you much better vertical sweep coverage.
But the operational cost and complexity sound staggering. Our sources detailed the scheme in the North Sea Magnus field, and it sounds like a complete nightmare to manage.
It truly illustrates the tightrope these engineers walk. You can't just flip a switch. The changeovers between injecting water and injecting gas take 3 days.
3 days each.
And they have to be scheduled precisely. More critically, they have to keep the field pressure within this specific, extremely narrow window.
High enough for the gas to stay in that critical, miscible state.
But low enough not to exceed the safety pressure limits of the production equipment.
Given that immense operational cost and the 3-day delay just to switch fluids, does that incremental barrel of oil you get from WAG ever become uneconomic? Does the cost of all this complexity just wipe out the profit?
That is the perpetual calculation. For many fields, the cost is worth it. But that complexity often drives engineers toward chemical solutions that might be simpler to control, even if they're expensive up front.
Which brings us to chemical flooding.
Right, like polymer flooding.
Okay.
Polymer flooding is strictly aimed at tackling the coverage problem, that macroscopic challenge. They pump these high molecular weight polymers into the water.
To make it thicker?
Essentially, yeah. It makes the water much thicker, slows it down, and forces it to sweep the reservoir more evenly instead of just channeling through those easy paths.
The limitations here were eye-opening. High cost because of the sheer volume of chemicals. They break down if the reservoir is too hot, above about 70 degrees Celsius.
Then they can even shear or be damaged just as they're being injected.
Which is why the gold standard for chemical methods is often alkaline surfactant polymer, or ASP, flooding. This sounds like it combines all the tools.
It does. The polymer handles the coverage, making the water thicker. And the surfactants and alkali, they go to work reducing that capillary trapping and surface tension.
So they're solving the microscopic problem.
Exactly. It's incredibly tailored. It requires a highly specialized design for the specific chemical makeup of that one reservoir. But the economic insight is powerful. For onshore fields, the incremental cost can be as low as $2.42 per incremental barrel.
So when oil is selling for $70 or $80 a barrel, that marginal barrel is highly profitable.
Provided you get the chemistry exactly right.
So we're seeing engineers fight this battle with everything from physics to high-end chemistry. But what about techniques that are, simpler, maybe less disruptive? What's on the cutting edge right now?
We're seeing a shift toward techniques that require less complex chemistry or mechanical intervention. And one surprisingly simple but effective idea is low salinity water injection.
So you're not adding chemicals, you're just changing the water you're already injecting.
Exactly. You strip out some of the specific salts and divalent cations like calcium from the injected brine. It's deceptively subtle.
What does it do?
This small change modifies how the reservoir rock and the oil interact, and it makes the sandstones slightly more water wet. This subtle modification mobilizes trapped oil without needing expensive surfactants.
That sounds like a dream EOR technique, low cost, low complexity. But the timeline involved tells a different story about industry caution.
Oh, absolutely. The systematic lab studies proving this mechanism were happening back in the 1990s. But the journey to a proposed large-scale field deployment like the Clare Ridge project in the UK took a staggering 17 years.
17 years?
Proving a subtle new recovery mechanism works reliably at a massive scale takes decades of verification.
And finally, let's talk about attacking those thief zones without having to drill new holes.
That's where deep reservoir flow diversion comes in. If you can't fix the channeling of the water, you just block the channel entirely. This technique improves sweep efficiency by injecting these temperature-triggered polymer particles that block the high permeability pathways deep in the reservoir, sometimes over 100 meters away from the injection well.
That's clever. It forces the water to go where the oil actually is.
Exactly. It's a targeted plug, and it's a crucial evolution. Older systems only plugged the pathways right near the wellbore, which the water would just flow around.
Okay.
By placing the block deep in the reservoir, it actually requires less upfront, expensive reservoir characterization and simulation.
Which significantly speeds up the planning phase.
Right.
So for decades, the focus of the entire global industry was on this battle of incremental improvement, fighting molecular physics and geological complexity to squeeze out marginal barrels, the $2.42 barrel, the 41% overall recovery.
Yes. And then horizontal multi-stage hydraulic fracturing, or HMSHF, arrived. This technology didn't bother with the microengineering of old fields at all. It bypassed the problem entirely by unlocking immense unconventional deposits.
This wasn't just a technical achievement. It was an economic revolution that fundamentally redrew the global supply map. Let's just focus on the scale of the disruption in the U.S. alone between, 2008 and 2013.
The production surge was massive. U.S. HMSHF production just jumped. It went from an estimated 750,000 barrels per day in 2008 to nearly 5 million barrels per day by 2013.
So by 2013, fracking accounted for nearly half of all U.S. crude oil, condensate, and natural gas liquids production. It was an overnight supply shock to the global market.
And that shock immediately suppressed prices internationally. The analysis we looked at estimated that without the U.S. shale surge, international Brent crude oil prices would have been anywhere from $12 to $40 per barrel higher in 2013.
$12 to $40 higher.
The prices would have averaged $122 to $150 per barrel.
Now, stop and think about that for a second. If you were driving in 2013, you were paying significantly less at the pump. Not because of some geopolitical agreement or decreased demand, but because of a technological breakthrough happening deep in the American heartland.
And that price suppression translated directly into massive consumer savings. The data estimated that U.S. consumers saved between 29 and 94 cents per gallon on petroleum products in 2013 alone.
And when you look at the cumulative effect over those 5 years, from 2008 to 2013, the total estimated consumer savings reached between $165 billion and $624 billion.
That range is just breathtaking.
Hundreds of billions of dollars staying in the pockets of consumers, all due to the speed and efficiency of this new extraction method.
And beyond consumer pockets, the geopolitical shift was dramatic. Increased domestic production meant the U.S. reliance on non-Canadian foreign crude imports dropped by 2.6 million barrels per day between 2010 and early 2014.
Just that one shift.
That single shift resulted in a nominal $66 billion improvement per year in the U.S. balance of payments. It was a trade and energy security sea change.
This technical abundance, the $2.42 per barrel marginal EOR barrel, and the flood of cheap shale oil, brings us to the core intellectual change in the energy world.
It does. The decades-long existential worry about peak oil.
Right.
It's just strategically replaced by the worry of peak demand.
I remember that peak oil fear vividly from the 1990s. It was driven by geologists noting that new large discoveries peaked way back in the 1960s.
Right.
The math was simple but terrifying. By the 90s, we were only finding one new barrel of oil for every 4 we produced. It really seemed like scarcity was inevitable.
But the current consensus proves that geological scarcity is not the limitation. The ultimate amount of available oil is determined almost entirely by economics and technology.
If the price justifies the operational complexity or the investment in unconventional extraction, the oil becomes available.
Exactly. And technology is now so advanced that it actually provides an effective price cap on crude oil, regardless of short-term scarcity fears.
You're referring to gas to liquids or GTL?
GTL is a powerful concept. It's the process of chemically converting abundant natural gas into liquid fuel. Historically, building a GTL plant was prohibitively expensive. We're talking $100 billion per facility.
But innovation has brought the cost of building these plants down to as little as $10 billion.
That's a 90% cost drop.
And that technological leap has brought the production cost of GTL fuel down to under $20 per barrel.
And this is the key piece of leverage. It means that if crude oil prices rise much above that $20 per barrel mark, the market will naturally start to switch to GTL fuels derived from natural gas.
It puts a fundamental ceiling on the price of crude oil. because a cheaper functional substitute exists.
And we have decades of supply for that substitute. The world's estimated reserves of natural gas could produce about 1.6 trillion barrels of oil equivalent. That is enough to fuel the world for approximately 60 years at current consumption rates.
So supply is no longer the issue,
Not at all.
which means the entire focus of major energy agencies, like the International Energy Agency, shifts entirely to peak demand. The problem is no longer geological. It's existential.
Yes. Humanity's use of oil emits 12.5 gigatons of CO2 annually. Climate mitigation requires an immediate, rapid decline in those emissions.
So the existential threat to the energy industry today is not running out of oil. It's having vast amounts of oil that nobody's allowed to buy.
This is the danger of stranded assets, production facilities, and reserves that lose all financial value if policy or consumer preference causes demand to fall too quickly.
And we had a stark preview of that financial collapse during the 2020 global pandemic shock, didn't we?
We did. It was a massive stress test for the entire system. It caused collapsing valuations, industry bankruptcies, and you had major energy players like BP writing off $17.5 billion worth of assets.
That wasn't a shortage crisis.
No, it was a demand crisis.
We started this deep dive with the frustrating low recovery rates in old fields and saw the incredible ingenuity required WAG, ASP, deep flow diversion to solve those microscopic and macroscopic technical issues, leading to hard-won incremental recovery. We then saw how one disruptive technology, fracking, completely reshaped the economics of extraction, leading to massive consumer savings and global supply assurance that was, previously unimaginable.
The cumulative result is that the limitations on oil supply are no longer dictated by geology or whether we can technically pull the oil out of the ground. They're technical, yes, but they're increasingly driven by new economic price ceilings like GTL and policy and climate pressure that limits the very desire for the product. Understanding the technical complexity of EOR alongside the price dynamics of fracking really illuminates the tightrope the energy industry is now walking between maximizing technical recovery and preparing for an inevitable policy-driven demand collapse.
So we discussed how traditional EOR is challenged by technical and economic difficulties, requiring specialized chemistry and immense operational costs for only modest incremental recovery. Yet, our sources mention one long-proposed method that hasn't been widely applied: microbial EOR.
Right, using microbes to modify the reservoir itself.
If high-cost, high-complexity technological ingenuity continues to hit these ceilings, could simple, cheap biological engineering, using tailored bacteria to alter wettability or flow, be the ultimate low-cost answer to recovering the vast remaining oil, even as the world transitions away from fossil fuels?
It's a fascinating thought to consider whether the simplest solution could be the last one tried.